next time, because there won't be time to face all of it. Okay, folks, I would like you to fire up your AnyLogics. Those who need computers, they await you in the back, arrayed on the cart there. Today we are going on for a very brief glimpse, a brief look at, in fact, third type of modeling that we'll be seeing within this class. And this is called discrete event modeling. And this modeling will accompany us for this and the next lecture. This sort of modeling has a very different perspective on modeling. And unfortunately, while it's a very, very well subscribed perspective, it's not one we're going to be able to spend nearly the amount of time on with agent-based modeling. We will revisit it. We'll revisit it when we're talking about hybrid models. But I want to give you the essential glimpses of it. I should note that for those in 394, time was not long ago, perhaps 5 years ago and before, where this sort of modeling was the only sort of modeling discussed within this course. And it's a nod to the fact that it is very popular in certain quarters, particularly areas of industrial engineering, understanding flow of factories, flow of hospitals and care facilities. And we'll get a little bit of flavor of that now. So our tool for this will be AnyLogic. And I'd like you to load up a model called Trauma Center. Okay? If you go to the example models through the help menu, you can call up the example models page, and there'll be one of them, a tab on the left says healthcare, and you'll want to select that. So let me see if I can. I closed it, but you should be able to select it as from the set of models under healthcare. I think it's the very first of them, if I'm not mistaken. So here, healthcare, examples on the left, and there's the trauma center. Okay? And you'll notice that's marked as what's called discrete event. This type of modeling goes by many names. Frankly, I find many of them confusing. Discrete event modeling, network modeling. My preferred name for it, which some others have adopted, is process-centric modeling. You'll see that it's very centered on the processes that operate on what we call entities, on these sort of mostly passive agents, as it were, that flow through the system. AnyLogic allows us to actually have a rich hybrid models where those agents can be active, but in traditional modeling, they're mostly passive. Okay, so we just loaded in Trauma Center, and we should see something like this. And ladies and gentlemen, I would like to propose that we run this model. So you'll see there's several pieces of it, emergency care, emergency department, etc. And we run this, and we'll see there's a little facility here, and individuals are coming into the facility either as walk-in patients or occasionally as ambulance patients. Walk-in patients, they come in, they present for some work with a registrar. They, in some cases, have to go back to a waiting room, and then they're brought in, and they're accompanied by various staff through the facility. So there's a nurse's waiting room here, and this may be a nurse's, so I'd have to read this. I think these are specialists here. And there's a set of rooms that are resources for seeing patients. And there's actually little bars that indicate what fraction of the time those rooms have been occupied. Some of them are diagnostic facilities and are used for more specialized cases. Others are general examination rooms. You notice when people come in, they're often accompanied by others. In this case, there's a specialist with the patient. Here's another specialist seeing the patient. And eventually, the patients complete their visit and are escorted out of the facility over on this side. This is the express care, I call it emergency, it's express care area of it, and generally we see these flow. You notice it's keeping track of the number of people who came in, people are waiting here, and I could slow it down and see this in more detail. But what we're seeing here is a rather different picture than we've seen, at least at the surface level, than we've seen for many previous models. We're seeing an irregular geometry, irregular facility. We're seeing, to be sure, what look like agents, but they're in very defined roles. We're seeing resources, resources associated with rooms, resources associated with diagnostic equipment, resources associated with staff who have to see a given patient. And if we look behind the scenes at this model, what we'll see is actually quite some defined processes mapped out in this flowchart type fashion, with some of whom have names that are suggestive of their purpose. So seizing a room, moving to the room with a nurse, getting prepped by a technical nurse, presumably for some imaging, some treatment by a doctor, for example, determination if a specialist is required, if so, treatment by a specialist. This is mapping out a process. And I want to highlight that it needs resources at certain times. And there's actually queues that are formed if those resources are not available. So we're seeing a type of modeling that is in many ways process-centric. It's focused on these processes. And individual patients flow through here. If we were to speed this up, we would see these numbers incrementing. Numbers indicating the number that have come through this particular place here. For example, there have been 16 that have not required specialists. And whether the equipment is portable or not, one has been portable, that's been required, otherwise not. So portable X-ray and otherwise. Here's someone that came in who does not require a specialist. So people are flowing through here, but more as passive entities. They flow through, they get treated, they get operated upon, they get imaged, and they flow out of the facility. Okay? This highlights many of the essential features of this system, but it's a bit complicated to take in at a single time. After all, this has many moving parts to it. Motivated by that, and having seen that glimpse, I'd like to suggest that we load in a simpler model. And I put this model up on Moodle, on the Moodle site for the class, and I'd like to suggest that you think about downloading it in the coming minutes, because it will illustrate things in a more easily digested fashion. Yes?
So if I were to kind of make a comparison right away, it sounds like system dynamics, or whatever you want to call it, the agents, quote unquote, they don't make decisions themselves. They're kind of forced around by external.
In this sort of modeling?
Yeah.
You're saying in this sort of discrete event, it's called a process-centric modeling. By and large, that tends to be quite true. They tend, in some cases, they are faceless, anonymous units that are sort of routed through this. They're not always patients. I don't want to give you the idea that this is always applied to patients. It's applied to modeling cars being produced in Ford's assembly line, or widgets being produced in factories, or doses of vaccine making it through a pharmaceutical production line, or what have you. And so, by and large, though, the entities we've seen here in this sort of these sort of facilities like this and here, yes, they're more passive. They are operated upon. They flow according to rules. They have very little agency associated with them. They are routed around, and they await their necessary resources to proceed with the patient. And I think all of us can relate, having been in institutions before. Sometimes we feel that we're living a very constrained sort of situation, that we just have to await the availability of resources, and only then will we get processed. And it's very much that sort of situation. Now we're going to be looking at hybrid models that go beyond that, where they can take a more active role. But this is very much the perspective of traditional discrete event modeling, that we have these entities flowing through, resources, availability and not, allow them to proceed on this process. And a lot of the interest is how many flow through and how quickly and how long, what are the delay times associated with that process. Is that helpful?
I think so.
Yeah. Okay. So I've highlighted some of the features of it just in my components there. A piece that I want to highlight is that often these entities will be persistently associated with resources. Those resources will accompany them. Think about a nurse accompanying you in a facility, pushing you on a gurney, or taking you to a room for testing and being with you through the procedure and then escorting you back to a waiting area. This is that's an aspect of what we call attachment. They travel with us, but we also will reserve those resources. Even if they don't travel with us, a room will be reserved for us, and then we'll be escorted to the room. Okay? So central concepts here: entities flow through processes, and they're processed at successive stages. Flowcharts specify this process. They specify this workflow that operates upon entities. And resources are required for processing. So in order to flow through that, you need resources to be available. Maybe it's a room, and you await a room. Maybe it's a nurse, and you await a nurse. Maybe it's a piece of diagnostic equipment, a portable x-ray machine, and you await the availability of that before they can do their work. So resources are required, and if there's no resource available, you await it. You're in a queue, conceptually, awaiting that resource. And typically, that's the name of the game here. We're interested in how does resource availability and to some degree resource placement physically affect flow. These entities that flow through interact with resources. They reserve them through a process known as seizure. They are associated with that resource. They're assigned that resource, assigned a room, assigned a scope, assigned a piece of diagnostic equipment, assigned a nurse to accompany them. But they also are attached sometimes, so they travel with these things. The bed goes with them. The nurse goes with them. There's going to be physical homes for resources. And people are going to move along movement paths. We actually saw that implicitly when people are moving around. They travel along paths. They don't go through walls, just travel through walls. They go along certain defined paths. And actually, anti-logic allows us to draw out what those paths are. Okay, so an important concept within this context is going to be the notion of a network, which groups together, ladies and gentlemen, entities, these quantities flowing through the system. Here, patients. In other cases, cars or partly assembled cars. Resources, these might be rooms. They might be fixed things. They might be things that are portable, like a portable x-ray machine. They might be things that have agency, that are mobile and have agency, like a nurse or a doctor. So it groups together the entities, the resources, and also portions of the workflow. There's those flow charts. Certain of them will be associated with certain networks. Others will be associated with other networks. Think about going from one ward to another ward. You'll be associated with different sets of nurses, for example, when you go from one ward to another. Go from the emergency department to a critical care unit, for example. Okay. So we're going to have a network, and in any logic, a network is indicated as shown. And that network is associated with a set of resources. Those are shown here. For example, doctors, procedure rooms, or scopes. I'm looking at this ophthalmology example. To allow us to appreciate some of the texture of what we're talking about, I'll run this ophthalmology example here. I'm going to start with simulating it for main phase 1. So right now, and you may not have noted this before, but each simulation anti-logic can be associated with a particular active object, in this case sort of a main class, we're associated with main phase 1, which is the simplest form of this. It's a teaching model. It's a model to sort of build up intuition. So we show the very simplest case here. Agents come in, they come into this area, they go to a room, and they leave. And that's all. And you see this set of nurses and this set of scopes here. So they come in, they move to a procedure room, they undergo some procedure, they move out, and they leave the network. Boom, done. But we can associate this instead with main phase 3, which is a more sophisticated thing, okay, more sophisticated rendition. And in this case, the agents have a more articulated process. So they come in here. I'm going to slow this down here a little bit. But here we have the nurses. Here we have scopes. And there's a patient who comes in. Let's see if we can get another patient in here. Okay. So what happened is the nurse went and grabbed a scope, came and got the patient, brought them to the procedure room. They're examining right now with a scope. And when it's done, when that procedure is done, so they're in this procedure room right here, they seize the resources, the scope and the nurse. The nurse got sent to the storage, sent to the patient. They attached to the patient and brought them there. They went through a procedure, and then they detached so they could travel independently. They returned the scope, and they released the agent. And poised down here for reasons that will remain obscure as a fighter jet. But there was some animation. People were interested in how you would animate, associate people with different shapes. Okay, so that was an example that's going to be illustrated through some of these slides to ground you. So in this case, we have doctors, so they're doctors, excuse me, not nurses. They have procedure rooms and scopes. And that there's a pool of each of these, a pool of more or less interchangeable ones. The idea is there's some group of doctors, and any doctor could see a given patient. There's a set of procedure rooms, and a given patient could be assigned to any of them. And there's a set of scopes, a pool of scopes that are available. And these entities flow through the state chart. Does that make sense? There'll be these operators that operate upon these entities, that make things happen to them. Right? They get treated, they get diagnosed, they get imaged, they get associated with that scope or whatever. Okay. So entities are the parties in which these processes operate. Think about patients in a hospital or clinic, cars in an assembly line. They're predominantly passive. Things happen to them. That's kind of the traditional perspective. Again, AnyLogic is a particular tool of breaking this down a lot, but that's the traditional kind of perspective here. We have these entities flow through the system. They flow around these state charts. They're injected into the system at a source, and they disappear at a sink, and they only exist for the duration of time that they exist in the system. This is not like our agent-based model where the agents stay all throughout a simulation often. Instead, they appear on the transom of the clinic. They're in the clinic for some period of time. They leave the clinic, and they disappear. And that's it. Okay? So typically you have multiple entities in the system at a given time. And those entities interact in one primary way. Merely one way. They interact by consuming resources whose lack of availability might interfere with the progress of other agents. So those agents are not, spreading infection via another. They're not talking. They're not transferring information. Instead, the fact that one of them is there means they're going to get a procedure room that otherwise would have been assigned to someone else, and therefore that other person will have to wait. That's the sort of mode of interaction. They're consuming resources that are needed by other entities. Is that clear? This notion? They do interact. I mean, there's some big difference. How quickly you flow through going to make a big difference. Are there 100 people already there or nobody already there? But the interaction is very limited compared to an agent-based model where they're sending messages to one another. Yeah.
So it sounds like the agents, if you will, they're
entities.
Consuming resources, or entities are consuming resources, and they're kind of fighting each other. So it sounds very much that it's a competition kind of model.
that's what it often, that is the perspective that it's often accompanied. That's not quite maybe a zero-sum game is kind of appropriate in the sense that you have limited amount of resources, and there's sort of rationing of these resources that, there's only so many resources to go around, only so many nurses, procedure rooms, and diagnostic equipment, and we want to make the system as efficient as possible given those resource constraints in terms of how it treats patients or the quality of care afforded to those patients, how long they have to wait. So when you hear about waiting times, and facilities and so on, this sort of modeling is sort of the first type that people often turn to. Okay, it's not the only type. I have a student working right now with the Ministry of Health, using system dynamics, for example, for it, and but this is a very popular type for that. And there's sort of this competition for resources, but there's often a need to kind of figure out rationalization. Who do these resources go to? How to prioritize certain people that might otherwise be at risk because they have to wait and they're really sick and they might otherwise, experience adverse events, and so we want to treat them extra quickly. And those sort of things can be looked at with this modeling, very much so. So, yeah.
A follow-up question then.
Yeah.
It seems very much so that the entities are only consuming resources. Is it possible that the entities can contribute to the resource pool?
Normally that's not done. Again, with any logic, you can't do that. You could have them bring knowledge to the system, feedback to the system that might improve the system in some way. They might help make a doctor who's examining them more efficient because they carry with them an electronic medical record, or they can convey some information about their history that would otherwise be guessed at, and therefore they can make the doctor's choices more effective. You can do that, but basically what it requires is making entities into agents and sort of enriching, basically bringing together agent-based modeling and discrete effect modeling. And we're going to be looking at exactly that issue in a later lecture.
Okay, cool.
Yeah. It turns out you can use subclassing in this context to maintain extra information on entities. So if you want them to maintain information on how long it took them to go from A to B, you could do that by subclassing them and just recording, oh, you passed this point, oh, you passed that other point, and you could accumulate statistics, for example. Entities are associated with a physical representation at many points, which travels around with them, and we saw that. So entities are the primary parties, the primary quantities in which the processes operate. Resources are required to proceed through those processes. So those entities need resources to make it through there, typically. To pass certain places, they need resources. They need, in order to be examined, they need that room to be in which to be examined. So resources are frequently required to initiate things. A doctor is needed to administer surgery, right? A piece of diagnostic equipment is needed to image a patient. A kidney is needed to get a transplant, right? An EKG is needed to record information from a patient. A gurney or bed is required for a patient. And AnyLogic, as well as other packages, makes distinctions between different types of resources. Not all resources are the same. Not all resources are equivalent in their functionality. Some resources are fixed. Think about a room, right? It's a fixed location. Some resources are portable. We can move them around. A scope, we saw that. But a scope doesn't move on its own. A scope needs to be carried. And so it's a portable resource. By contrast, some other resources, doctors, nurses, staff, etc., have agency, and they can move around on their own. You could tell them, go here, go do this, and then go to this other location. Go get the scope. That's what we just saw. Go get the scope and bring it to the patient. That's something one of these mobile resources could do. Okay? It's still a resource. It's an ancient entity, And you see there's kind of this dichotomy. There's kind of these entities that kind of flow through, and then there's resources needed to process the entities. And very definitively, there's this kind of divide between them. These are mobile resources, okay? They're a different sort of thing than the entities, okay? And we noted that networks are often associated with multiple source resources. So we saw that, for example, within our model here, that down at the bottom, there was this declaration of a network as having these set of resources. So those are mobile, doctors. Some of them are fixed, some are portable. Does that make sense? Yeah. Yeah, it's fundamental to particularly fundamental to the flow diagrams here. So if we look at these flow diagrams, these flow diagrams are entity-centric. They're written from an entity's perspective. Okay. The operators here are operating upon an entity. Now, those operators may require a resource. For example, this network seizure. This is something which seizes a resource in the network. In fact, it seizes several. It seizes a procedure room, a doctor, and a scope. Those resources are then reserved for that entity. When we say seize, it has this transgressive sound to it, but really what it means is we reserve them. It's an old term, but we allocate those, or we assign those to this entity. Okay. So this entity is therefore assigned a procedure room, a doctor, and a scope. But you notice, Jason, that this assignment it's kind of it's occurring to the entity, and the entity kind of conceptually carries that with them. They're associated with these resources, and then the doctor is sent to go get the scope, and then the doctor is sent to the patient. Okay. This is a network sent to. They're sent to the entity to whom they belong. Okay, and both the doctor and the accompanying scope are sent there. And then the doctor is attached to the patient. In other words, in fact, all of the resources, the scope and the doctor, are attached to this entity, which is then sent to the procedure room. So these operators are written from or articulated from from the entity's perspective. And these resources kind of accompany around the entity because they're attached to them. It's the entity that's kind of the center of attention. Things are getting done to them, and the resources are attached or detached to them. The resource, their life is very constrained. Their life is depicted in as much as they are servicing this entity. But they're not off doing, whatever during the other time. They just kind of serve there. Oh, an entity has come. Let us go serve. And they go and they serve that entity. And the entity flows through here. This is all very entity specific. They flow through, they leave, and as part of this, they release resources who go back to their home locations. But these actions are actions operating upon the entity. Does that make sense? Okay, we'll see this a little bit with some of the operators in more detail. Great question. Other questions? Okay, so time is a-ticking. So we're talking about these resources and resource pools associated with things. And each of these resource pools is associated, they can be capacitated, meaning they have a certain capacity associated with them. And in this case, we define some capacity associated with them. In this case, 5 things. Now, you'll notice that, and this is just a sort of a peek at something we'll get to later, they also have a speed associated with them. They travel with a certain speed. A resource travels with the speed. An entity travels with the speed. But they are different things. And there the twain shall meet. I mean, in the sense that it's really written from an entity perspective. You don't have resources becoming entities. And you'll notice there's a type for each resource in this pool. There's a quantity, there's a type. Is it static? Is it fixed? Is it static? Excuse me. In other words, it's fixed. Is it moving? In other words, that is agency and can move, or is it merely portable? And there's some capacity. Okay. So we have these flowcharts. These flowcharts have some start. There's a set of these operators. The icon indicates the type of operator being applied, and there's a small set of different operators available in the palette. And then there's a sink at the end when the entities disappear. Entities, their life is delineated between these 2 points. Okay. If we want to think about capturing, people get discharged from the hospital and they go home and then they may present for care. Like if they didn't receive adequate care or they were discharged early, they may come back for care. To really represent that, we need to hybridize this with an agent-based model so they don't just disappear into thin air at the end. There's some persistence. Okay. So we have flowcharts can be hierarchical. This whole area here can be expanded into a flow associated with CAT scans, for example. And they're frequently nonlinear. We saw that early on, but they can have branches. And those branches, sometimes they go one way, sometimes they go another, based on some condition. Okay? Okay, so over here in the palette, in AnyLogic, I think it's in the enterprise library, you'll find various types of operators here associated with this sort of modeling. Okay, and we'll illustrate some of the main ones here. I think, given the time available, I'm just going to do a brief overview of this today, and we'll afford it greater time next time in our Thursday. So major operators of interest, I'll just walk through these. And hopefully this will reinforce and sink in a fuguish fashion. So we have sources of entities. Sinks, so entity sources out of which the entities come. Sinks, out of where they disappear at the end. I spoke about those. We further have network enter-exit. They get associated with a certain network. This network that groups together resources, it groups together physical locations, it groups together, and it's associated with some number of operators within the network, for example. So think about a ward, which has different numbers of people. So when they come in here, they go into a network, and that then alerts them to a set of resources associated with that network. And they can leave a network and go into a different one dynamically. Okay. They can select an output. So in other words, which way they go here could be dictated by some condition. In this case, there might be a probability associated with it, for example, or you might just say if the condition is true. So you say, if this entity has this characteristic. Now, normally entities have very few characteristics, but you could have something like that. Or it could be a condition based on how many patients are there in the facility right now. If it's really busy, we'll route them this other way. We have a delay associated with some procedure, something that has to happen. It takes a certain amount of time to undertake this procedure, for example. Someone is seen for an HPD workup, for history and some physical workup and some diagnosis. That may take some time they have to spend in a room, in a procedure room. Okay. Now, I've highlighted a bunch of operators that are not particularly resource related. Indirectly, we enter a network, it has resources because of that. But the real key ones are these ones over here, the resource operators. And I want to highlight, and we'll go back and hit this next time, the distinction between the different types of operators. Some of them have to do with reservation. We reserve a resource for an entity. Entity focus. Reserve it for this entity. So here, we associate an entity in some resource. And we call this network C's, or its opposite, really, is unreserved. Alternatively, we may want to attach a resource to a person. Why would we attach a resource to an entity? Well, we want we want the doctor to travel with that entity to a given location. So when the entity attaches to that doctor, and then the entity moves to a procedure room, that doctor will come with them. They're attached to a portable resource, like a scope. And when they move, that scope travels with them. So there's a particular logical reservation where they're simply associated with, they're assigned to this resource. Oh, you're assigned that room over there, but you're not necessarily in the room. You're assigned a nurse, but that nurse isn't yet with you. Reservation has to do with the first of these. Accompanying is a separate matter. And for that, they go to them and they're accompanied by them thenceforth. Moving the entities, moving the entity to a location, like to a procedure room, or moving a resource, like where we move the resource associated with them, reserved for them to go get the scope so they can provide them with the scope up front. Okay? So those are the major operators here. And we'll talk more about these next time. We'll examine how this works in a little flowchart. And then finally, we'll get a glimpse of how all this comes together to yield this sort of animation, this sort of visual representation that we saw, where we have people coming in, and you have this movement between facilities, and this whole kind of visual representation showing what's going on. Okay? So we're going to see that next time. So that was a bit of a glimpse of those operators, and we'll talk more about them in more detail for the next time. Thank you very much. Hey, thank you.
Sorry, I was late. Somebody threw down the gauntlet of the Excalibur at Louis.
Oh.
So I had to finish that up.
So I hope you're feeling good.